Here we have question 5 that is based on organic chemistry, naming of compounds. So that is the first part under the section. Now question 5 says the letters A to G in the table below represent 6 organic compounds. It is always important for you to analyze the table that you're given, analyze those compounds, understand which homologous series they belong to by identifying their functional groups. Once you have that information, then it's okay for you to go on to the questions, because by then you know more or less what's happening and you've answered most of the questions already. So starting off with A, we see that we've got carbons and hydrogens, and then we notice the presence of a chlorine. That immediately tells us that A is a haloalkane. Now going on to B, what they've given you there is the condensed structural formula, so we don't see the bonds being shown. But we notice that we've got this oxygen in the middle of the compound. That has to be a ketone. For C, we've got 5.6-dimethyl hept-2-ine. So our suffix here, ine, tells us that this is alkynes. Now for D, we notice the presence of this OH at the end, so we know that is an alcohol. In E, you've got HO at the end. Now when it comes to condensed structural formulas, when it has HO, that is an aldehyde. If you see OH, OH is generally an alcohol, but HO is an aldehyde. And then for F, we've got 2.3-dimethyl pentan-2-ol. So the suffix here, ol, tells us that is an alcohol. Okay, so now that we understand which homologous series each of these compounds belong to, we're now ready to go on to the questions. 5.1 says, write down the IUPAC name for compound A. So let's have a look at compound A. In order for us to write down the IUPAC name, we need to identify the longest parent chain. So let's count. We've got 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4. Now if we go the other way, we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So at one point we did count 5. So 5 is the longest parent chain. And to get 5, that has to be your parent chain. So here you have the first carbon. Here's your second carbon, third, fourth, and fifth. Now we can identify our branches. So we see that, yes, we've got the chlorine. So that's going to be a chloro. On the second carbon, we've got a methyl. On the third carbon, we have a methyl as well. Please remember that when it comes to naming your compound, especially when you're naming your branches, that part particularly, branches have to be named alphabetically. So if we've got a chloro, we've got a dimethyl, we have to talk about the chloro first. So chlorine is on the first carbon, it's going to be 1-chloro. We've got methyl on the second and the third carbon, so that's going to be dash 2,3 dash dimethyl. And the parent chain had 5 carbons in it, so the parent name is pentane. So that is the IUPAC name for compound A. Now for 5.1.2, they want the letters of the compounds that are functional isomers of each other and give a reason for the answer. Firstly, functional isomers that we work with, there are only 2 types. We've got carboxylic acids and esters, they go together, and we've got ketones and aldehydes. Now, from compound A to F, we did not come across any ester or any carboxylic acid, so we know it's definitely not that. But we notice that for B, B is a ketone, F is an aldehyde, So those two are functional isomers of each other. So our answer is going to be B and F. But what is going to be the reason for this? We can use the definition of a functional isomer to state that as our reason. We know functional isomers are organic compounds that have the same molecular formula but different functional groups. Now for 5.1.3, they want the letter of the compound that is classified as a tertiary alcohol. Give a reason for the answer. So we have two alcohols on this table. We've got D and F. So just to show you why the answer is not D, if we look at the carbon that contains the hydrazole group, this carbon is directly bonded to one other carbon only. So compound D, alcohol D, is actually a primary alcohol. The only other alcohol that we have to work with here is F. So the answer has to be F. And if you had to draw out the structural formula of compound F, then you would see that the carbon containing the hydrazole group is directly bonded to 3 other carbon atoms. So that's something that's not so evident from the IUPAC name itself. So if you write out the structural formula, you'll be able to visualize it so you can actually see why it's a tertiary alcohol. So there we have it. Now in 5.1.4, they want the structural formula of compound C. So when it comes to drawing out the structural formula, it's always best to start off with the parent chain. So in this compound, we notice that the prefix of the parent is hept, meaning that the parent chain contains 7 carbons. So we start off by drawing our basic parent chain structure of 7 carbons. The next thing we go on to is the functional group. Here we have -2-ine. Your suffix "-ine" tells you that this is an alkyne, and on the second carbon, we are expecting to have that triple bond. So I'm going to count these carbon atoms left to right. So here is my second carbon. So on the second carbon, I will have the triple bond. Now, before I go on to the branches, I'm just going to go in and fill in the rest of the bonds, making sure that each carbon atom has only 4 bonds around it. So here we have it. Now, obviously, on your second and your third carbon, where you had the triple bond in between them, they now have 4 bonds around. So you cannot actually put hydrogens at the top or at the bottom of those carbons. Okay, now we're ready to go on to the branches. We've got 5,6-dimethyl, meaning that on the 5th as well as the 6th carbon atom, there are going to be methyl branches. So since I've worked left to right with the numbering, I'm going to work the same way. So on 1, 2, 3, 4, 5, I'm going to put the methyl branch at the top. And just for the sake of having enough space and my compound doesn't end up being too squashed up, I'm going to put the methyl branch for the 6th carbon at the bottom. So now that I've got the parent, now that I've got the functional group as well as the branches, I'm going to go in and fill in all of these empty bonds with hydrogen atoms. So this is your complete structural formula for compound C. We're now on to 5.2. It says compound D is heated with an organic compound P in the presence of concentrated sulfuric acid as shown in the equation below. So to understand what's going on, let's just go back to compound D and see what that was. Okay, compound D was an alcohol. And think about all of your reactions. Now this is actually based on the third part of organic chemistry, which is the reactions part of it. The reaction that uses an alcohol, reacts it with something else in the presence of H2SO4 as its catalyst. That has to be esterification. So just to help us out, I've labeled these. Compound D is the alcohol. P would be a carboxylic acid, so we know how esterification works. You've got an alcohol reacting with a carboxylic acid in the presence of H2SO4. So H2SO4 here is your catalyst. And that produces an ester, so Q is an ester and H2O is water. Okay, so it says the compound Q that is produced contains 9.80% hydrogen, 31.38% oxygen, and 58.82% carbon. So what we actually given here is the percentage composition. We know that together C, H, and O makes up 100% of this compound. But they've given us the composition in terms of its percentages. Now 5.2.1 says write down the empirical formula of compound Q. Support the answer with a relevant calculation. Empirical formula is something that goes way back to grade 10 when you were first introduced to stoichiometry, also known as quantitative aspects. You learned how to do empirical formula. So we're going to follow the exact same procedure. However, what we notice here is that these elements, hydrogen, oxygen, and carbon, they are not given in the correct order. So using the percentages as the masses, here's what we get. All we did was we replaced the percentage sign with grams, with G for grams. Your next step is to get number of moles for each one of these compounds, and to do that we're going to use number of moles equals mass over molar mass. So for carbon we're going to have 58.82. Molar mass of carbon is 12. We'll calculate this just now. For oxygen it'll be 31.38 over 16. And hydrogen is 1, so basically being divided by 1, it does not change. So that's going to be measured in moles. Okay, let's calculate the other two. So here's what I get. Also notice that I have not rounded off. The reason why we don't round off is because we are going to create a molar ratio, and every number after the decimal is important to ensure that we get accurate values. Your next step is to create a molar ratio with these values. So here's what we have. And at this point, we divide throughout by the smallest value. So if we look at all three, the smallest value here is 1.96125. Now when we start simplifying each part, we put the first fraction on our calculator. Now here it gives you 2.499 and it continues. But normally what we're looking for are whole numbers. If it was 2.9, we could easily round off to 3. But the fact that it's 2.499, if we round off, we get 2.5. If you have a value that is 0.5, you cannot round it off to the next number. So it would be absolutely wrong for us to round this off to 3. 2.5 is too far away from 3. So in terms of rounding off here, if it's a 0.5 value, leave it as is. Okay, so we leave it as 2.5. Second fraction gives us 1. Third fraction, we get 4.996. That can easily be rounded off to 5. So the question is, if we need whole numbers, but we get 2.5, what do we do in that case? Now to change a 0.5 value to a whole number, all you have to do is multiply it by 2. But what you actually do is you multiply the entire ratio by 2. So every single value gets multiplied by 2. Doing so, what we end up with is 5 is to 2 is to 10. Now, since we have whole numbers, we can use that as our empirical formula. So remember the order that we're working in: carbon, oxygen, and then hydrogen. So it actually doesn't matter what order you work with. if you worked with the same order that they gave you, which was actually hydrogen, oxygen, and carbon, that's perfectly fine as well. But when you write down your empirical formula, the order there needs to be correct, okay? For esters, we're going to have carbon first, so we're going to have C5. Now you can either put the hydrogen and then the oxygen, or the oxygen and then the hydrogen. They're not too fussy about that, but here's what I'm going to do. I'm going to put the hydrogen first and then the oxygen. Okay, just to show you, it can be written like that, or we could have C5O2H10. So either one of this is fine as your empirical formula, as long as you have carbon first. I would actually go with this as my answer. So the reason why I would go with this is because think of your general formula. CnH2n plus 1 COOH. So if you think about it, the format there has carbon, then hydrogen, and then the carbon with the two oxygens and the hydrogen. So if you're just following that format, you've got carbon, hydrogen, and your oxygens kind of come last in the compound. So this would be the more correct way of representing this molecular formula. Now 5.2.2, they want the structural formula of compound Q. If we just refer back to this reaction, compound Q is an ester. Now obviously, compound Q is going to be made up of the number of carbons that D and P together have. If we just go back to compound D, it contained 3 carbons. So just remember here, compound D has 3 carbons. We've calculated the molecular formula of compound Q. So if we refer to our formula, compound Q has 5 carbons in total. So Q here has 5 carbons in total. What does that tell us about compound P? The carboxylic acid should have 2 carbons, because obviously the 3 carbons from the alcohol and the 2 carbons from the carboxylic acid should give us 5 carbons in the ester. Now, understanding how many carbons the alcohol and the carboxylic acid is made up of allows you to draw the correct ester. So the ester is going to have 3 carbons from the alcohol. So let's draw those 3 carbons. That would have the O on it as well. Let's not forget the hydrogens. And 2 carbons from the carboxylic acid. So that's going to be a carbon with the double bond oxygen and another carbon with its hydrogens. So this is the structural formula for compound Q. Now 5.2.3 says the structural formula of the functional group of compound P. So remember, compound P was a carboxylic acid. This is what the structural formula of the functional group of the carboxylic acid looks like. You've got the carbon that has the double bond oxygen, the single bond OH, and remember it has to have 4 bonds around itself. So this is the carboxyl group. Please remember to like, subscribe, and turn on your notifications for more content.